we're all here. So our meeting's recording now. I'm going to make sure the video is not going to be backwards. Oh.
Go back and watch the meeting later? Or?
Yes.
Okay.
Yeah. So I record them. Now, let me tell you, I don't know if you checked last time. Ooh, why did it get so, did it get large? Maybe it's the same. Maybe I'm just crazy. Last meeting, I recorded it, but you know, I had my second device and I recorded from that instead of this. So when I went to upload it to D2L, like it was just a black screen, the whole video, like 35 minutes black screen. So if you did check the video from last time, what I ended up doing is I teach this class right after this. So I just uploaded that one so you can see everything we still did.
Nice.
But I've got it right this time, guys. Okay, so I'm going to, no, wrong way. Okay, so I'm going to try this. So in the first class, I used like a real small portion of the board. I didn't know how much, you know, zoomed out I could be or anything. I'm going to try to do it this way, and you guys can kind of gauge me since you guys can see what the Zoom meeting people are watching. And extended class, if it looks blurry or weird or something like that, let me know and I'll zoom in a little bit. Okay, so first things first, I gotta get a really, really good marker. Okay, that one's pretty good. Okay, so we're gonna move on a little bit today. So remember last time we talked about limits and I showed you some pictures. We talked about what I meant by the word approaching. So I said, as x approaches a value, what is the limit, or what is y approaching? And we talked about approaching meaning from both directions, because it's not specified. If I say I'm approaching, but I don't specify from where, I have to assume from everywhere. So approaching is both directions. Approaching also, in a mathematical sense, means that I could get infinitely close. And we talked about what it means to be able to get infinitely close to a value. So I'm going to draw a graph similar to what I did last time. So we've got this here. And I'm going to make it a little squiggly. I'm going to put one of those holes in it and a jump. Okay. So we looked at a graph like this last time. We did, right? Mm-hmm. I know I did it in my second class. I want to make sure I got as far. But what did we talk about was happening here? Let's say that this is x equals 1. Let's say the y value up here at the dot is 1, but this hole is -5. You guys, the limit of this problem as x approaches 1, what did we say happened there?
It's undefined because it splits.
Right, it's undefined because I can't say that my graph is approaching a specific value just from all directions, right? Okay. Because from the right, it looks like it's approaching 1. Mm-hmm. Cool. From the left, it looks like it's approaching -5. And that was a problem because we had that discrepancy. Well, today, so let's write that down. So from last time, if I asked you the limit as x approaches 1 of this function we'll call f of x, I said it didn't exist or it was undefined. Well, we're going to define it a little better today, because what I'm going to ask you is I'm going to ask you for the limit as x approaches 1, but I'm going to add a little bit extra notation on it. I'm going to put a little plus up here in the corner by the 1. So it's a superscript. It looks kind of like a power. It is on the right side of the number. But this plus indicates that I want to approach 1 from the right. So anytime you see the plus, it's from the right because right values are positive and larger. If it was a minus, which we'll look at, that means coming from the left. So as x approaches 1 from the right, what is the limit, you guys? As we come from over here, approaching 1 from that positive side, what would your answer be here? It would be 1, because just on that side, that makes sense. We are approaching 1 from the right. So the limit of this function as x approaches 1 from the right is 1. It is defined because I've specified a side. So what if I have this one? I want to take the limit as x approaches 1 again, but now I've got a minus up here. So from the left. So coming from the left, what are we approaching?
Approaching -5, but it never.
Right. So it never hits -5, but remember it does get infinitely close to -5. So it's good. We can say that from the left, our limit is -5. So that's something we couldn't do before. And of course, the double-sided limit, if it's not specified, we assume both sides, that's never going to exist. But if I do want to talk about a limit at this point, I can specify and say which direction I'm coming from, and both values will exist, and they will be different. That's the whole reason why the double-sided didn't exist. Yes?
Is there a way to notate, since in this example, it will never reach -0.5, is that 0.5 or 5?
-5.
-5, since it will never reach -5, is there a notation for that it like?
No, so the limit, we don't, it doesn't really matter if it hits it or not. If I asked for like f of 1, well, actually f of 1 would be up here, but let's say that it just didn't exist at 1. Then f of 1, that actual point, you'd say, oh, that doesn't exist. There's no value there. But when we talk about a limit, all I'm concerned about is just the approach. It's more like, I don't care if it really ever makes it there, but I want to see what it's getting close to. Okay, so let's look at another graph. Let's learn something else new. All right, this one's going to be fun. Okay, so this is different, right? Do you remember from algebra what's happening here, this dotted line I've notated on a graph, what that's called?
Asymptote.
Right, it's an asymptote. It means that for some reason, and let's call this x equals -2. For some reason, whatever the role of this function is, it doesn't exist. Nothing, there's no output at -2. Which in my last graph, I had a hole, so why could I not just make it a hole? Well, it's because at the asymptote, it's kind of like a jump point. Notice the graph on this side is going down, and it is an arrow, so that means that as x gets closer and closer to -2, this graph is just going down towards -infinity forever. So it's going to get infinitely close to that value, but it's never going to touch it. But the problem is the graph is just going down to -infinity. It's not approaching any certain value. So notice the jump. Beyond -2, it looks the same, but these two pieces never touch. This one's going down forever. This one's going down forever. And then the graph goes on from there. So this isn't just a hole now. This is like, you can't cross this line. The graph on this side and the graph on this side are never going to touch each other, which makes it hard for our limit, because remember, our limit's all about what is it approaching. So when I talk about an infinite limit is what we're going to talk about. Now, there's a couple ways that different people look at it. And one of the biggest pet peeves I have with your particular book is that in section 1, it'll tell you that, well, it's not approaching anything. Approaching an infinity doesn't count, so it doesn't exist. But in section 2, it says, oh yeah, we'll call that -infinity. So we are going to go with section 2. I like to be able to define it as much as possible. this limit, even though it's never approaching a specific value, and it'll never actually stop. We're gonna say that a limit like this, as x approaches -2, and from both sides it's doing the same thing, we're gonna say it approaches -infinity. So it's a little bit of a misnomer. Oh, that's the worst infinity sign I've ever made. Because when you think about a limit, again, you're thinking about what value am I getting close to? It's kind of like what's the border? Like there's always an end point. I'm so close to this and the graph stops instantaneously, just instantaneously at that one point. But that's not happening here. It's almost like it's unlimited, it's unbounded because it goes down forever. Yes.
Is that basically saying that line is continuing to go on forever because it can't cross the asymptote?
Yes, so it goes down forever, and as it's going down, it's getting infinitesimally close to this asymptote line, but it still never touches it. So it will go down and slightly to the right forever, but it'll never hit that line at -2.
So how do you recognize which one you're dealing with, whether it's a negative infinity or whether it's a number that it's approaching?
Okay, so when you're approaching a number, if this approached a number, it would stop somewhere.
Okay.
So it wouldn't have this arrow that says, oh, I just go on forever. It would actually have a point where it stopped. Maybe it doesn't exist there, but it would stop somewhere. But this doesn't stop. So this is unbounded. Why did I say -infinity instead of just infinity?
Because
line's
it's below the one.
Going down.
Right, it is going down. So we are going to differentiate between a -infinity and a positive infinity. But when you have a graph with an asymptote, as long as both sides are going down toward the same infinity, so in this case, they're both going down to -infinity, we are going to label this as -infinity. We're not going to say it doesn't exist. It kind of doesn't exist, to be honest. It's like saying putting a limit on a graph that is unlimited. Like I said, it's unbounded. It goes down forever. But we're going to say that because it offers more information to us than just saying, oh, it doesn't exist, it's undefined. You know, this at least tells us what it's doing. You know, if somebody wasn't looking at the graph, they could picture that. They could know what's happening at that point. So what if I have an asymptote line on a graph? Let's say that on this graph, our asymptote line is going to be at x equals 4. On this side of the graph, I'm going to come up like this. So it looks like it's going toward positive infinity as it approaches 4. But something happens from one side of 4 to the other, and this part of the graph actually comes from down here. So this actually happens a lot. There's a lot of functions that are graphed like this. So I want to talk about 4. So the limit of this function, oh, what am I doing? That's weird. This function f of x as x approaches 4. All right, so it looks like on this side, I'm going up to positive infinity. And on this side, it's going down to -infinity. So what could I say about the limit as x approaches 4?
Say, like in a notation form, positive infinity, comma negative.
Right, so if I have, well, I have to specify which one. So again, like the one where we had the two sides going to different things, if I specify, hey, from the left it's doing this, or from the right it's doing this, even the infinite limits still are bound to that definition that says if you don't specify, you have to look from both directions. So, right, this one's not going to exist. It's not because it's infinite, it's because the two sides are not converging. But what if I ask you the limit as x approaches 4 from the right. So sometimes the plus and minus can get confusing because when you see this, you say, oh, right. Remember, it's not going right, it's from the right. So you're actually following the graph left. So be really careful about that from the positive side of 4. Right, your limit would be, you could say negative infinity because it's going down that direction. And then as you approach 4 from the left, what's our limit? Right, just positive infinity. So you guys, even though they're both infinity, because they're both different directions of infinity, the 2-sided limit still is not going to exist.
What were the difference between those two graphs? That, I mean, because like right here, you only did it from the left. Why did you do it on both sides of this graph?
Oh, I did a 2-sided limit here. So notice I didn't specify which way I was going.
Mm-hmm.
So that means I have to look from both sides, but both sides are going to the same place.
Okay. And then on that one, since both sides aren't going to the same place, that's why it's undefined.
Yes, that's why. So the 2-sided, if I have to look at both sides at the same time, they're not reaching a meeting point, right?
Mm-hmm.
But if I look at one side and then the other, I can define each separate side. So yeah, if you ever don't see anything here, just remember you have to consider both sides. It's more restrictive, right?
On the positive 4, the one that comes from the right, how do you know that it's not going to be like that arrow is not going up? How do you know that it's going to be negative?
So because it's from the right, you look at, so whatever your value is, think about, okay, I'm going to look at the positive side of that value, but I'm still approaching 4. So notice from over here, I have to actually go down to the left to approach the 4. If I followed it this way, I'd be approaching
From
other
the left.
values.
Okay, that makes sense. Thank you.
That's just the coolest thing. Like,
Yeah,
anyway.
that is pretty neat. So pretty much if there's never like a point on there, it's almost always going to be an infinite symbol because we're not approaching a specific place.
Right, right. So anytime that the X value I picked for you has an asymptote for one, that's a big hint right there. You're gonna have an infinite. Now, those are the only times you're gonna have an infinite limit is at these asymptote points. Because those points are the only places that allow for these functions to do something erratic like that, to either just shoot down really fast or shoot up really fast.
Because asymptote defines that it's never going to cross. If it didn't say it's an asymptote, or it would be assuming that those
Yeah,
points
I'd
will
assume that it
have to
would
cross at some
meet
point.
somewhere, absolutely, yeah. Yes,
In the example with the hole,
Mhm.
are those 2 points touching? Is there no jump in between them, or?
it depends on the problem, but sometimes they meet at a hole. And
Mhm.
sometimes, like the first example I did, there's a jump. So remember, if there's a jump, you would have to specify which side you were going from. But if they both met at the same hole, then the limit would exist at that hole. So you guys, we're gonna move away from graphs. Graphs are great for explaining limits, and I think it's the best way for you to really see and understand what we're doing. But a lot of times we need to be able to find the limits of a function without looking at a picture. And it's harder because I can't explicitly see, I can't follow the line, right? I can't say, oh, it's going toward this value, you know? I have to do it algebraically. You're gonna find that it's easier than you might think it would be because we have some really nice rules. So the first rule, algebraic rule of limits, we call them properties. It's going to be the property that we talk about when we're trying to take the limit of a constant. Okay, so when I say a constant, I mean just a number, something that doesn't change. So for example, if I gave you the function f of x equals 5. Notice there's no variable here, so you can put whatever value you want to in for x, and as x is changing, y is never changing. The output is always 5. That's what it means to be a constant function. If I made a quick sketch of this graph, remember what it's saying, y is always 5, or the output is always 5. You pick what you want for x, but every point is going to have a y equals 5.
Horizontal line.
Yes, so every constant function is just really a horizontal line. So that's the function we're working with. Let me ask you to find the limit of something. So I want to find the limit of, I actually labeled my function, I don't have to call it f of x this time. So you guys, this is the first time we've actually had a function with an equation attached to it, right? So when I just draw a picture, I just called it f of x. This is an actual function, the function equals 5. So when you write your limit notation, you actually put that whole function in there, and I know it's just one number. So I would say the limit of 5, the limit of this function, that's just a 5. Let's go as x approaches 2. You can look at the graph since that's the way we know how to do it. Let's say here's x equals 2. What happens? What are we approaching on the y's as x approaches 2 from both sides? 5, right? Because it never changes. So I'd say, oh, that's definitely 5. Oh, but what if I want you to find the limit as x approaches negative 125? Right, I'm like, oh crap, I can't see it on my graph. Doesn't matter though, right? Because this function's rule says the output is always 5. You can approach whatever you want. The answer is always going to be 5. So you guys, this is our first property. If you're looking at a constant function, which I know it's just a number, it's hard to want to call that a function, but every number is just a constant function when it's in function notation. So if I ask you the limit of 5 or the limit of 7 or the limit of 9, it doesn't matter what I put down here. It doesn't matter if it's one-sided or two-sided, or it doesn't matter. Your answer is going to be that constant. So in a more general form, let's say that f of x equals just any number, k. So k is a constant. It could be any number you can think of. Positive, negative, fraction, decimal, it doesn't matter. If your function equals k always, then the limit as x approaches any value, let's call it a. So a is any value you want x to approach. Of this function k, your answer is always going to be k. So this is a general form of writing that property. Whether this makes sense to you or you like seeing it in a hard example, either way is fine. This way just says it doesn't have to be 5. It doesn't have to approach 2. It can approach anything and be anything. So the limit of a constant is itself. So that makes sense intuitively. But the functions we work with are not all just single numbers, right? I mean, that would be a super boring semester. We're not in the market graphing a bunch of horizontal lines for 4 months. So let's learn another property. Let's get a variable in there. Let's talk about the limit of the identity function. Does anybody remember what the identity function is? Okay, so y equals x. So you probably learned it as y equals x. Remember, we are in function notation. So in function notation, f of x equals x. So basically, the simplest form of a function I can find that has a variable in it. What does the identity function do? What does it mean y equals x? Do you guys know what this graph says? If y and x are the same, if x is 1,
Single point center.
well, if x is 1, what's y? 1, because they're the same. What about if x is 2?
2.
Then y is 2. You guys, what we get is a line with a slope of 1 that goes straight through the origin. Just your basic linear function. So this is the identity function, and it says that no matter what you choose for x, y is going to be exactly that same thing. Okay, so let's think about a limit. So this is our function, just an x. I want to find the limit of the function x as x approaches 5. Without even looking at a graph, knowing what I know about the identity function, how x and y are always the same, as x approaches 5, what do you think y is also approaching? It has to also approach 5. So if I ask for the limit as x approaches -29 of x, what's the answer going to be? It's going to be -29. So you guys, another really intuitive type property, it makes a lot of sense. I will say, you've got to be careful and not get the two mixed up. So when you have the x here, remember your answer is going to be what x is approaching. Your answer comes from down here. Remember in the constant, your answer was the function. Your answer was up here. So you just have to be really careful. Talking it through always helps. Say, okay, y and x are always equal. So if x is approaching this, y is also approaching this. All right, so those are some key things that we need to remember, but even though we put a variable in there, we're definitely going to be looking at functions that are more than just x, right? So what we can do is we can actually extrapolate from these two basic properties to find values for tons of functions, because if I know how x works, and I know how any single number works, what are functions made up of? Numbers and variables, right? So I think I can probably figure this out. The problem comes in how you combine values. So let's talk about, what if I had a number multiplied by a variable and that was my function? I know the number part and I know the variable part. Do I just multiply them together? Is that how that works? Or do limits have some kind of special relationship? Luckily, it works like you think it should work. Let's talk about that should be a P. I was just gonna write product. Okay, let's talk about the product property of limits. So first, before I give you this property, I'm gonna have to give us two separate functions. So let's say I've got a function f of x and a function g of x. These functions could just be constant numbers. They could be x's. They could be really elaborate functions, but either way, they are functions of x. One is called f and one is called g. I want to find the limit of f of x multiplied by g of x. So maybe it's a constant and an x multiplied together, like I mentioned before. Maybe it's a large polynomial function times another large polynomial function. It doesn't matter. It's two functions multiplied together. I want to find the limit. You guys, let's say as x approaches a, I can find the limit of each one separately and then multiply those two values together. It works just like I want it to work. So the limit of f of x times g of x is going to equal the limit of f of x multiplied by the limit of g of x. So you can find the two limits separately, and multiply those values together. Notice the x approaches a. It's just we're approaching the same value, right? If we were approaching a value on f of x and then a different value for g of x, that would ruin this whole thing. You do have to be approaching the same value for both functions. So let me show you an example of that. I want to find the limit as x approaches 2 of the function 3x. It is one function. I say, oh, well, there's just one function there. It's just 3x. But remember how small our building blocks are. I can say this 3 is its own function. It's a constant function. And the x is an identity function. There's two functions multiplied together. And I want to find the limit as x approaches 2. So my property says that I can break it up. It says that I can take the limit as x approaches 2 of the 3, and then multiply that by the limit as x approaches 2 of the x. So I want to break my functions down to their core foundation. Now, are these values that I know how to find? This is the limit of a constant function, and this is the limit of the identity. Those are the one things that I know how to do. All I had to do is break it up into those pieces. So let's keep answering the question. Let's take the limit of the constant function 3 as x approaches 2. What is that answer? It's 3, right? Remember that function always equals 3. So it's going to be 3 times 2, right? The limit of x as x approaches 2 is 2. And I get a 6. Now, let's think about it for a second. Do you think I would have gotten that same answer if I had just thrown a 2 in here for the x? Absolutely, guys. If x approaches 2, I say, oh, well, let's see what happens when x is 2. I put a 2 in here, I get 3 times 2 is 6. Seems easier, right? You guys, it's absolutely true that you can do that with certain restrictions. So, yes, breaking up, every time you take a limit, you can break your functions up into their building blocks, like take the numbers away from the x's and stuff like that. Or you can recognize what type of functions we're looking at, and it'll help you. So, this is true. It is true that if I had just stuck a 2 in here for the x, I still would have gotten a 6. I didn't know that I could do that. And the reason why I can do that, remember, let's look at this function. 3x. It's just a line with a slope of 3 that goes through the origin. 1, 2. Here's your 6. You can see it happening. Why is the limit I got the exact same thing as if I had just put a 2 in for x? So if you put a 2 in for x, you get 6, no matter what. Whether you're taking a limit or not taking a limit, it equals 6 there. The limit as x approaches 2 from both directions is also 6. Both sides are getting infinitely close to 6. The reason why these two values are the same is because my function is constant and smooth. It doesn't do anything crazy, right? It doesn't have a hole here. If that was a hole, then I couldn't just stick 2 in for x and get an answer, right? It doesn't have a hole. It doesn't have an asymptote. It doesn't have a crazy jump. It does exactly what you think it's going to do. That's why its limit and the function value there are exactly the same. Functions like this have a name. Smooth, constant, wonderful, predictable functions. We call them polynomial functions. Those graphs that I drew for you with the holes and the jumps, those are hard to have an actual equation for. Like, you just draw them and say, oh, this probably is some kind of function. Like, it's actually hard to take an actual function algebraically and get a graph with a bunch of jumps and holes in it. There's only a couple ways you can get a hole in a function graph, or even an asymptote. So I'm gonna go over those ways, and I'm gonna tell you what to look for, and if you don't find it, you're looking at a nice function. Polynomials, guys, these are functions where all or any that exist, powers of x are positive and whole. So let me give you some examples of a couple functions. We're going to say if they're polynomials or not. Okay, so if I give you a function f of x equals 5x cubed plus 4x squared minus 3x plus 5. It's not a function I like to deal with usually, but could I say it is a polynomial function?
Yes.
Yes, because any power that's on x is either it's whole and positive, right? I don't have any negative exponents, and I don't have any fractional exponents. So just by looking at this, I can say, yes, this is polynomial. What does that do to help me? Well, it means that the graph of this function will not have any holes, will not have any weird jagged areas or jumps, and it won't have any asymptotes. Because it doesn't have anything crazy, if I ask you to take the limit, let's say as x approaches 2 of this function, because I know it's polynomial, because I know it's not going to do anything crazy, I can absolutely just stick a 2 in for all those x's, because I know the answer at 2 is going to be the same as what it's approaching at 2. Basically, it goes where you think it's going to go. So let's find it. Taking the limit as x approaches 2 is as easy as putting a 2 in for every x value. So we do that. 5 times, make sure you do the power first. 2 cubed is 8, so 5 times 8 is 40. 2 squared is 4, so 4 times 4 is 16, minus 6 plus 5. So 56 minus 6 plus 5, I get 55. I don't know if you guys can see that. Oh, yeah, they did. Okay, so I got 55. That is the limit. If you graphed this and looked at the approach from both sides of x equals 2, you would approach 55, and the function would equal 55 there. So you guys, we can only hope that all of our functions are polynomial, right? Because then taking the limit is as easy as plugging a value in for x, and for the most part it is. But why, we're going to do one more, you guys, that's going to be a problem. Okay, is this function polynomial? It's a little hard to say because the powers on x are there and they're both 1s, and it looks like it's okay. It looks like they're whole and positive. Why is that not positive?
Because it might not be depending whatever.
Right, like there's a place where this doesn't exist. You know, if I put a 3 in there, that's a problem. But the power looks whole and positive, so what gives, right? It's because it's on the bottom, right? So while this is a 1, it's not really a 1. It's a 1 because I've stuck it on the denominator. I could rewrite this. Like this, right? Because we know how negative exponents work. If it's negative, you send it down to the bottom so it looks positive, and you could send it back up. You guys, this is not a whole and positive exponent. Yes, whole, not positive. So when you look at any function that has x in the denominator, you say that's not polynomial. I can't just stick in a value. Now, sometimes it's going to be interesting because sometimes I will be able to, but sometimes I won't. So what we like to do is we have, I think I have enough time. Woo. When it's not polynomial, you have to use properties. I have a quotient here, so I'm going to use what we call the quotient property. So what I mean is the limit of a function over another function. That's what we have here. It's not polynomial, so I couldn't just stick it in, so I have to rely on a property. So, you guys, it's exactly what you think should happen, just like the product rule did. If you have the limit of f of x divided by another function g of x, you can take the limit of the top and the limit of the bottom separately and just divide those two values. There's a catch, right? The catch is, this is provided, oh, sorry, this is g of x. I saw confused looks, and I didn't know why, but now I do. You guys, the problem is, this only works as long as the limit of g of x is not 0. Why is that the case? What if it was 0? It'd be undefined, right? And then I would just have to stop and say, oh, it's undefined. So let's use our quotient property up here and see what happens. Now, I haven't told you what x to approach yet. You guys, if I want to take the limit of this function as x approaches 2, let's use the quotient property and see what happens. So that says that I can take the limit of x plus 5 and take the limit of x minus 3, both as x approaches 2, I'm just not writing it, and divide. This property is going to work this time because I get to look at them separately. So when you take the limit of x plus 5, is that a polynomial function? Just by itself, x plus 5. Absolutely. So what can I do? I can just stick that value in for x. So remember, x is approaching 2, so I put a 2 in here and I get a 7 on top. Easy peasy. Now I can look at the bottom limit separately. Is x minus 3 a polynomial function? So looking at it separately, like by itself, it's not on the bottom of anything. Is it a polynomial function? Yeah, by itself it is. So it means I can put just a 2 in here and it'll be fine. See guys, what's 2 minus 3? So that's weird, I got a limit on that one. Sometimes you will. You have to use the property, but sometimes it works. Just sticking in x. When will it not work? Right, this is a problem. You guys, you can use the quotient property until you're blue in the face, but it's not going to change anything, right? You're going to put a 3 in here and get an 8 on top. But you're going to put a 3 in here and get a 0. You guys, this is just a bad case. This is going to be undefined. Now, there might be values on that graph that it's approaching. Like if we could see the graph, maybe it would be better. But algebraically, if I want to approach 3 on that graph, I have to say the limit doesn't exist or it's undefined. But if I was approaching anything else, I could use the quotient property. All right, guys. Ooh, right on time. Look at that. All right. That is it. If nobody has any questions, and I will see you on Friday. So the first way we did it, we broke it up using the properties. And that's something you can do on all functions.
So I got it.